Students, in the previous video, you know what is work, heat, internal energy in thermodynamics. Thermodynamic variables like pressure, volume, temperature are there, which are used to describe the state of a thermodynamic system. But students, you can take any two variables out of pressure, volume, temperature to describe the state by indicator diagram or through graphs. One can show how the state of a thermodynamic system is changed. That's why your indicator diagram is there. So what is an indicator diagram? This is a graph through which the state of thermodynamic system is described, and in this case you use only two variables out of three. If you use pressure, volume, then we say PV diagram. Automatically the third variable, temperature, can be obtained from these two. So students, what is an indicator diagram? This is the graphical representation of state of system with the help of two variables. So students, what is indicator diagram? This indicator diagram is nothing but we can write a graphical representation of state of thermodynamic system with the help of two variables. So it is a graph through which you show the state of the system, and in a graph we require some variables. Here we take two variables from pressure, volume and a temperature. So if I take PV, pressure and volume, this is called PV diagram. So what is this PV diagram? It is a graph, it is a diagram between pressure and volume of a system. Suppose I take the graph like this. Along y-axis I take pressure, along x-axis I take volume. Suppose the graph is like that. If this is in this direction, you see volume is increasing. If the graph is moving, the volume increases, means expansion. Suppose this point is P1, V1. This point is P2, V2. I mean, the initial pressure is V1, initial volume is V1, final pressure is P2, final volume is V2. The state of the system or gas is changed from P1, V1 to P2, V2. So this is called your PV diagram. Since volume increases, students, you see, if this is the case, volume is increasing. Since the graph is like that, arrow is in this way, so here volume is increasing from V1 to V2. V1 is small, V2 is large. So due to increase of volume, your gas is expanded. If I make the graph like this, if the graph is like this, students, you see, arrow is in this way. If arrow is in this way, it is the case of compression. Gas is compressed, its volume decreases. Since it is moving in this way, the volume is decreasing. I mean, this is the initial volume part. This is the final volume part. I mean, final volume is, suppose this P2 pressure, V2 volume. Initial is P1, V1. Initial pressure, initial volume. Why it is initial? Because the graph starts from this. So this is the case of compression. Students, you know PV diagram, graph between pressure and volume of a gas or system, in which you know the state of the gas is changed. How? Here the initial pressure is P1, initial volume is V1. This is the initial state of the system. This is the final state of the system. This is the initial state of the system. This is the final state of the system. I mean, the state of the system is represented graphically. This is your indicator diagram, or one says PV diagram, pressure volume diagram. But students, what is the importance of this graph? In every graph, whether this is pressure volume, whether this is velocity time, whether this is position time, in any graph, two things are important. One is you take slope of this graph, means change in y-axis by change in x-axis. I mean, change in this, I mean pressure divided by change in volume. This gives the slope. Another is area bounded by this graph. This is the graph. This is the graph. So what is the area? That means if you draw this is the area. I mean this part is the area. So this shaded part is the area bounded by this graph with volume axis. This is the important part. So the importance of PV diagram is that the area bounded by this graph with volume axis is the work done by the system or on the system. That means this graph gives you work done. This work done may be positive or may be negative. If work is done by the system, we know positive. If work is done on this system, we know negative. So when work is done by the system, when a system or gas expands, but when gas is compressed, that is work is done on the system. So students, this is the indicator or PV diagram, and from this you can find out the work done. If you take the area, one questions how area is taken. Suppose, for example, you take the graph is like that. So you just draw it. What is this area? This is the area of a trapezium. Suppose one says the graph is in this way. So you draw it. What is this? Area of a rectangle. That means the graph makes area with volume axis. This is the area. This one makes the area. So this is the area of the trapezium, area of the square, area of the rectangle, in some cases area of the triangle. You know what is the area of those structures. So easily you can find out the work done. So what is the formula for this work done? Students, how to obtain this work done? You see, suppose I consider a container. It has a piston. At position 1, it contains gas or system. Students, you know gas has pressure, gas has volume, gas has temperature. So due to this pressure, it exerts force on this piston. So what happens? Piston will move to this position. So due to gas pressure, it exerts a force on this piston and this moves from 1 to 2. So what is the work done involved? So how to find out this? You know, force exerted on the piston is equal to pressure into area. Area means what is area of the piston? This is the area of the piston. So F is equal to pressure into area. Okay. But what is work done? Work is force into displacement. Since force and displacement are in same direction, force and displacement are in same direction, that's why it is fx cos 0. This is fx. This is pressure into volume. Of course, students, if I take a small work done here, it is dx. Why? Because if the displacement is very small due to gas pressure, if you take a small displacement dx, so small work done dw will be there, and accordingly it is changed. What is this? Pressure into dV. This is nothing but, students, P into dV. Here it is F into dx. Dx does not mean d is multiplied with s. Dx is a small displacement. dw is the small work done. dV is the small change in volume. Okay. So what you get? Actually you get dw small work done is equal to P dV. That means due to pressure of the gas, the piston moved through a small displacement dx and work done involved is this. But if this volume is changed from V1 to V2, suppose initial volume of the gas is V1. Now after piston movement, the volume becomes V2. So what is the net work done involved? From small work done, net work can be obtained by the method of integration. If you integrate this, I mean integration of dw is equal to integration of P dV from limit V1 to V2, it is 0 to W. This is called lower limit, this is called upper limit, this is called lower limit, this is called upper limit. Lower limit means starting point. Work starts from 0 and its final is W. I mean total work done is W. Similarly, volume starts from V1, ends at V2. So from left hand side you will get this will be W, 0 to W, that is P dV integration V1 to V2. Integration of dw is W, integration of dx is x, integration of dy is y. From integration you can know these things. Okay. So here I put W, this is lower limit, upper limit. So after putting this limit, you will get W is equal to P dV V1 to V2. So students, this is the formula of work done when the volume of the gas is changed from V1 to V2. So we get the mathematical formula for work done when gas is expanded or gas is compressed. I mean when volume of the gas is changed from V1 to V2. This is the formula for work done. Students, this is also taken as per expansion, because gas is expanded and volume increases, that is from V1 to V2. So we can also say this W is the work done of a gas for its expansion. Okay, students. Now next part is, what is the work from this graph? I have already told you work done can be obtained by taking the area bounded by this graph with your volume axis. Okay, what I have already explained. The next part is, if it is a cyclic process, suppose the graph is a cycle or it is a closed one like this. If I make the graph in this way, like this, volume, pressure, it is a cycle, closed one. The graph is A, B, C, D, A. It starts from A and ends at A. So it is a cycle. Suppose one makes like this. It is also a cycle. Suppose I make like this. It is a cycle. I mean the starting point and the end point will be same. So in this case, what is the work done? You have to remember, if you take the area of this one, this gives the work done. I mean work done is the area of A, B, C, D, A. In this case, suppose I am A, B, C, D. Also here, if you take the area of this square or rectangle, this gives you work done. Work is area of ABCD structure. Here you take the area of this triangle. I mean area of triangle is the work done. You know area of the triangle. You know area of the rectangle. You know area of the square. So easily you can find out work done from PV diagram if it is a cyclic process. So this is called a cyclic process. Actually students, how it is obtained? One says, sir, how this is obtained? Suppose in this case you take like that. Suppose this is M, this is N. So first you take area of A, B, C, M, N, A. This one, this area. So first you take this area. Next what you have to do? Take this area. For this graph, you take this area. Now subtract big area to this area, because the graph is this one and that one. So you see, take this area, then you take that area. From big area to this area, if you subtract, you will get this area. So that's why you take the area of A, B, C, D, A, you will get. Same process. Either one say Sir, I find out the big area, then I find out this area, then subtract. Can I get this one? Yes. Answer will be same. Similarly, in this case, the graph is like that. You take whole area, big one, like that. Big area. Then you take this area. Then you subtract, that area will be obtained. In this case also, you see. You take this big area. Now you take this area. If from big area you subtract this, you will get this one. Same result will be obtained. If you take individual one, area of this, area of that, then you subtract, then you will get the same answer. So therefore, when you see a cyclic process is there, your work done is the area of that loop. The loop may be a triangle, the loop may be a square, the loop may be a circle, like that. And another point to remember, because you know what may be positive or what may be negative. So in a cyclic process, if we see clockwise, for clockwise your work is positive. If a cycle is like that, it is in clockwise direction, then your work is positive, means work is done by the system. But if it is anti-clockwise, suppose in this case the graph is like that. Anti-clockwise, in this case work done is negative. It means work is done on the system. One says, what is the meaning of negative work, positive work? Suppose you find this work as 2 joule. So for this will be positive 2 joule. Suppose you find work for this as 3 joule. So this will be negative because it is anti-clockwise. So positive work, negative work, like that. One says, sir, if you find out individual one, same result comes. Yes, you find work done for this, work done for that, work done for that, also same answer will be obtained. But it will be easier or it will take small time if you take the area of this loop. Only you remember, if it is clockwise direction, then plus sign will be there, otherwise minus or negative sign. So students, this is your work done during a cyclic process. So in this video, what we have discussed, that is your indicator diagram, which is vital in thermodynamics. It is a diagram between pressure and volume. Your pressure and volume are changing from one state to another state of a system. And from this graph, you find out how much work is done. Whether this work is positive or this work is negative.